As we begin the 7th week, we are going to now look at even more advanced dynamics that waveforms can show. For example, what we will be doing this entire week would be about reflection and transmission of waves. I assume that there is some waveform that is propagating, let us say from the left hand side, from the far left hand side, and at x equal to 0, as it is shown in this figure, there is a change of medium. So, when the waveform reaches this boundary, part of it would be transmitted to the second medium. So, when x is positive, x greater than 0 would correspond to second medium, and there will be a part of it which will be reflected back into the first medium, which corresponds to x less than 0. So, x is of course the position, and since we are dealing with one dimensional waveforms, this alone is sufficient to talk about the dynamics of the waveforms. So, this is the standard scenario which we are going to work with. So, let us look at some examples before we actually begin our calculations. If we think of our standard example, namely the string, it is equivalent to saying that at x equal to 0, suddenly the material of the string has changed, because in all these problems where a wave is launched on a string, the medium is the string itself, and in the medium of string there is some waveform that is travelling. At x equal to 0, suddenly the string has changed. So, it is possible that, for example, you could have maybe a thin string for x less than 0 and a much thicker string for x greater than 0. So, suddenly the wave finds itself in a different medium when it crosses from x less than 0 to x greater than 0. That is one sort of example you could keep in mind. But there are many examples. For instance, routinely we will have to discuss things like what happens when light travels from one medium to another, or when sound waves travel from one medium to another. So, these are typical examples of when waves do meet the boundary between two different media, and they do travel from one medium to another medium, and there is also often, when such a thing happens, a reflection back into the first medium itself. Okay. So, anything that I speak in this room, a little bit of that is heard in the next room adjacent to me, simply because the waves generated, the sound waves, they go hit the wall, a part of it is transmitted and part of it is of course reflected back. So, I could say that in medium 1 corresponding to x less than 0, the impedance of the string is Z1, and in medium 2 corresponding to x greater than 0, impedance is Z2. So, when I say wave is going from medium 1 to medium 2, it is actually going from a string which is characterized by impedance Z1 to another string which is characterized by impedance Z2. We will continue to work with this wave equation and the solutions of these wave equations, which are simply y as a function of position and time. Now, the additional complication is that we are going from one kind of medium to another kind of medium. So, let me recap this idea of impedances. The problem was that I have a string. I do not need to worry about what is the boundary condition on other end of the string, but at my end I am giving it oscillations, and I am assuming that there is uniform tension in the string. So, the forcing that I am providing here at this point propagates as a wave through the string. So, in such a situation we equated the forces at x equal to 0. So, if you might recall this figure. So, at x equal to 0 we equated the forces So, the forcing external forcing was F 0 e power I omega t, and that is equated to the component of tension, which is minus t sin theta, where theta is the angle that this string makes with the horizontal. Now, of course, we work with the small angular approximation as usual. So, sin theta is approximately tan theta, which is dou y by dou x, just the gradient of the displacement at x equal to 0. So, we go through this derivation, we compute this dou y by dou x at x equal to 0, and finally, we recognize that there is a quantity impedance that is involved here, and impedance is simply rho multiplied by C. When we use impedance to characterize a medium, what quantities are involved? One is the linear density and other is the phase velocity. Together these two quantities characterize the medium. Physically, impedance is the resistance that medium offers to the flow of waves. At x equal to 0, I have my boundary. So, this is the boundary where there will be a change of media. So, for x less than 0, there is one media which is characterized by Z1, and Z1 from the formula that we made just now is rho 1 C1. Rho 1 is the linear density in that medium and C1 is the phase velocity. And similarly, in the region when x is greater than 0, the media is characterized by the impedance Z2, which will be given by rho 2 multiplied by C2. Again, rho 2 is the linear density in the second medium. So, I am going to have a wave that is coming in from far left. So, that would be my incident wave. And what are the various things that this incident wave can do? It comes from far left, hits the boundary at x equal to 0. There are only two things that can happen. One is there can be transmission. So, there will be a transmitted wave, and another possibility is there can be reflection. So, you can have a reflected wave. So, it is reflected back in the same medium, and for each of these waves, incident, reflected and transmitted wave, each of them are solutions of our wave equation. So, we shall start by writing down the solutions for each of these components. For us, string is the medium through which all this is happening. We shall assume that there is uniform tension T in the string. So, let me write the incident wave. So, you should remember that this displacement of the incident wave as usual will be a function of position and time. So, I should be able to write it as A1 into e power I omega t minus k1 x. Similarly, I can also write for the reflected wave, which is y r, again a function of position and time. So, in the case of reflected wave, it goes in the opposite direction. So, I need to change the sign of x, which is why I have e power I into omega t plus k x. So, that tells me explicitly that it is a wave that is going from right to the left, and all these are happening in medium 1 corresponding to x less than 0. So, now let me also write the solution for the transmitted wave, which will be as usual function of position and time. Now, you will notice that I have used same value of omega for the incident, for the reflected and the transmitted wave, but I have used different values of wave number k1 and k2, k1 for the first medium and k2 for the second medium. So, I should recall this idea that the frequency of oscillation is not going to change even across the boundary, that is going to remain the same. So, together as a coupled system, omega is like your normal mode frequency, it is not going to change. So, phase velocity, for instance, which I can indicate by C1 would be omega by k1. So, if you are in medium 1, both the incident and the reflected wave would have the same phase velocity, simply because omega is same and k1 is also same for both of them. On the other hand, for the reflected wave, the phase velocity would be a different value. So, that would be c2, which is omega by k2. So, let me go back and write these things here in our figure. So, this is y I and this is y r, the reflected wave, and this is y t, which is the transmitted wave. We need to put in some boundary conditions that would connect what happens at x less than 0 to what happens at x greater than 0. So, typically when you see such things happening where a wave goes from one media to another media, you will not see suddenly the displacement changing in value just because it is changed from one medium to another medium. One of our first boundary conditions should be that displacement across the boundary should be matched. It is another way of saying that displacement cannot be discontinuous at the boundary. You can't have a small displacement of the wave that is incoming and suddenly that produces a huge displacement on the other side. That cannot happen. Physically, that is not feasible. Second condition is what can be called a dynamical condition, namely that the transverse force, which is given by T into the gradient dou y by dou x, should be continuous. So, we have the physical system that is set up, wave going from one media to another media, there is part transmission, part reflection, and we have written down the solutions for each of those components. We have characterized each of the media, we have written down the solutions. Now, to bring them all together, we need some point of commonality in a sense, and that is provided by these boundary conditions. So, both boundary conditions are physically motivated, that displacement across the boundary should not be discontinuous. So, we put in condition that displacement should be continuous and transverse force should not be discontinuous. If it does, there would be net force. So, we avoid that situation and we put in a condition that transverse force should be continuous as well. Okay. Now, we are set up to apply these conditions on our equations. So, first of that says that displacement should be matched, which implies the following. So, I just need to put in x equal to 0 in these equations, and as you can see, it will give me a1 times e power I omega t plus a2 times e power I omega t is equal to b times e power I omega t. And of course, e power I omega t can be cancelled. That is one way of saying that e power I omega t cannot go to 0. Hence, it must be true that a1 plus a2 minus b should be equal to 0, which is equivalent to saying that a1 plus a2 is equal to b. So, it connects the amplitudes of the incoming wave, the reflected wave and the transmitted wave. So, that is the result of putting in the first boundary condition. So, I have put in the first boundary condition. Now, let us use the second boundary condition, namely that the transverse force should be continuous at the boundary, which means at x equal to 0. I can express this condition as now again, since we already know y I, y r and y t, I just need to differentiate all three of them with respect to x. I will get the following expression. So, I have the complete expression in front of me right now. It just requires one differentiation with respect to x to be done. Now, we need to just substitute x equal to 0 throughout. So, this is again second expression that we have, which again connects a1, a2 and b, and there is also k1 and k2 involved. Now, if you look at what is unknown in this, there are 3 quantities A1, A2 and B, but we seem to have only 2 equations. So, it appears as though that we will have to determine 3 unknowns from only 2 equations. It is true in a sense, but we really do not need to know all the 3 quantities. It is enough if we know each of these quantities as a ratio with respect to A1. So, now let me write both these equations in that form. So, I had A1 plus A2 equal to B. This would be can be written as 1 plus A2 by A1, which is equal to B by A1. Second of the equations is that minus K1 A1 plus K1 A2 equal to minus K2 into B, and that will give me minus K1 plus K1 into A2 by A1, which is equal to minus K2 into B by A1. Okay, so, we will keep these 2 equation aside for the moment, we will come back to this, but let me focus for a moment on this second equation. Now, what I want to do is to introduce impedances Z1 and Z2. So, you will remember that we said impedance Z characterizes the medium. So, somewhere the impedances will have to enter this equation. So, in fact, what we should do is go back and insert the T, which we actually cancelled off from this equation. So, let me rewrite this equation slightly differently. So, I am going to multiply it by T throughout, which is the uniform tension in the string, and this K1 will substitute by omega by C1 and K2 will be substituted by omega by C2. So, Z1 and Z2 are the impedances in the 2 media. Now, I can cancel omega throughout and rewrite it slightly differently. I can take Z1 common. So, that would be A2 minus A1 is equal to minus Z2 into B. So, now again I divide throughout by A1, in which case this equation would become Z1 into 1 minus A2 by A1 into Z2 into B by A1. Now, I have this equation, and from the other condition I have this equation. From this point onwards, I just need to solve for A2 by A1 and B by A1. One thing to notice with these results is that this ratios A2 by A1, which is the reflection coefficient, and the transmission coefficient, that is B by A1, both are independent of omega. It does not matter what your normal frequency is or what your frequency is. What if the second medium offers a huge resistance, which is equivalent to saying that the impedance of the second medium is infinity, extremely large. So, your intuition should tell you that if it is going to offer huge impedance, the wave should not be able to pass through into the second medium. We need to check if that is true coming out of the formulas. So, here if I go back to this formula, which is B by A1, the transmission coefficient, if I divide the numerator and denominator by Z2, I will have, so B by A1 would be 2 Z1 by Z1 plus Z2. Let me divide throughout by Z2. So, I will have 2 into Z1 by Z2 divided by Z1 by Z2 plus 1. Now, if you take the limit Z2 going to infinity, I am going to get a 0 in the numerator and Z1 by Z2 will be 0 plus 1. So, I am going to get 0 by 1 which is equal to 0. So, that tells me that the transmission coefficient is 0 if Z2 is infinity. It very much kind of agrees with our intuition that there should not be a transmitted wave if the second medium offers infinite impedance. At Z2 going to infinity, it is a simple exercise, simply divide by Z2 in the numerator and denominator. A2 by A1 will give you, let us say, Z1 minus Z2 by Z1 plus Z2, and if I divide by Z2, that would be 0 minus 1 divided by 0 plus 1, and that is going to give me minus 1. So, A2 is equal to minus A1. So, A2 is the reflected amplitude and A1 is the amplitude of the incoming wave. So, here nothing is transmitted, everything is reflected, and when such a reflection takes place, there is a phase change of pi. So, that is what we see here in this problem. So, the entire wave is reflected, nothing is transmitted. In the limit when z tends to infinity, r is minus 1 and t is 0. Say for example, this is my boundary at x equal to 0 and I have an arbitrary wave packet, something that looks like this, which is going in this direction. That is my incident wave, and when it hits the boundary, if assuming that Z2 is infinity and Z1 is some value of impedance, what we will see is that, so part of this wave has already been reflected and it comes out with a minus sign, and long after it has interacted with the boundary, the wave would look something like this and it would be travelling in this direction now. So, what I have drawn here is what happens when it interacts with the boundary, and long after all this has happened, you will notice that there is only one outgoing wave, which is exactly like the incoming wave, but sign of amplitude has changed. So, that is what happens if Z2 is infinity. If Z2 was not infinity, a part of this wave would have gone into the second region. In other words, the figure should have been drawn something like this. This is my incoming wave, and maybe when it interacts with boundary, there is a part that has crossed over with a different amplitude and a part that has gone like this. So, there would be a smaller amplitude wave here and another smaller amplitude wave here. So, long after it interacts with this boundary here, there is one part which will be moving in this direction, which is the transmitted wave with possibly smaller amplitude, and there is another one which is reflected, which is moving in this direction, probably smaller than the incident one.